it's now time to have Emily Riehl from Johns Hopkins in Baltimore. So you probably know her from the great service she did to mankind by writing this category theory in context book. I guess most of the young people in the audience learn category theory from there. But she's also doing higher category things and also higher categories in proof assistance and recently in Lean. And so she will talk about formalizing invisible mathematics.
Great, thank you. So thank you to the organizers. This is my first big proof conference. I'm very happy to be here. I want to start with two apologies. So first apology, I'm giving a lot of talks this month, and I was finishing the slides for this one about 5 minutes ago. So, so now I'm just going to wing it, and this is not quite up to my usual standards of preparation, so apologies for that. Second apology I actually made a slide for. So when I came up with the idea, it just appeared in my head for the title of this talk. It seemed a little bit familiar, so I Googled it and found it was the title of another talk that, in fact, I attended. I'm following, Kevin Buzzard gave me some advice a while ago that I should use a different color for links. So now everything in yellow is actually a hyperlink. I used to sort of, you would have to click random highlighted text and decide whether or not it was a link. Anyway, yellow is a hyperlink, so that's the link to this talk. So it's a great talk, that's why I want to highlight it as an apology. So, I mean, firstly, Andre Bauer is responsible for this wonderful Math Overflow post, which explains actually what proof assistants are and why they often use dependent type theory. Anyway, this is a great talk that talks about sort of the invisible mathematics that's involved sort of in the architecture of a proof assistant, going from the sort of vernacular language that a user uses to the formal language that's being checked by the kernel. He also talks about challenges of interoperability and then a bit of invisible mathematics in the sense that I'm going to use here. So that's another approach to invisible mathematics. So for the purposes of this talk, the definition of invisible mathematics I want to use is sort of pretty broad and non-specific, but maybe exactly to the point that interests us here, which is aspects of mathematics that are not visible in a pen and paper proof, but become visible in the computer formalization proof. And maybe the takeaway, which I expect many of you have discovered already, is that there's quite a lot of that, and there's sort of lots of different kinds. So, I mean, in particular, there's a lot of buzz around auto-formalization, and I guess I don't want to say anything that the AI folks here are going to disagree with or dislike, but as a sort of mathematician who's confronting with the human challenges of using a computer proof assistant, I think this invisible mathematics is something that is really going to hinder attempts at auto-formalization, because I think this is not something that we understand well as human, even the expert users of proof assistants, and I do not count myself as an expert user of a proof assistant. I'm a user of a proof assistant, but not an expert user of a proof assistant. So I think it's, for me at least, it's something very interesting to think about a little bit more and try to understand a bit better. Okay, so, and to illustrate what it means to go from a pen and paper proof to a computer formalized proof, I'll just briefly mention some experience. So this past summer, I was at the Hausdorff Institute Prospects of Formal Mathematics program and met Mario Carnero and a bunch of people here in this room for the first time. And one of the things that So this was the program where I started to use the Lean proof assistant for the first time, and I've been kind of resistant to using Lean because I came into computer formalization from homotopy type theory, which you can't do in Lean, and in any case it seemed like Lean was going to be a very difficult place to try and formalize the kind of mathematics that I do, sort of higher category theory, despite all the impressive things that can and are being formalized in Lean. But of course, having sort of in various venues said critical things about Lean for years, I felt like I should start to do some Lean formalization and be able to speak a little bit more from experience. And so in particular, I had a result that is, in the first section 1.1 of a book on infinity category theory that I co-wrote with Dominic Verdi. This is not our result. This is just a classical background thing. And specifically, there's a way to embed an ordinary category, an ordinary one-dimensional category into an infinite dimensional category that goes by the name of the nerve functor. It takes a category to a simplicial set that happens to be a quasi-category. And that was in MATLAB already. So Johan Kamelen, I think, or maybe, well, I think Johan gave us the nerve, no, Joel Riehl, sorry, gave us the nerve functor. But it has a left adjoint, which takes an infinite dimensional category, an infinity one category, and collapses it back to a one category, and that was not in MATLAB. So this seemed like a thing that Mario and I could work on together. I thought this would be relatively straightforward. So the definition, which is the first half of this page, is just the definition of the homotopy category, and the proposition is a proof that that is in fact the left adjoint to the nerve. It notes that this adjunction exists for formal reasons. Those formal reasons have to do with the fact that the category of categories has colimits. This was not in MATLAB, so the formal approach was not available to us, but we could just formalize the direct approach, which is explained in maybe 5 sentences here. So what did that look like in formalization? Well, we wrote so it took us 3 months. I mean, of course, this is not the only thing Mario did during that time, but we met, I don't know how many hours you think we spent working on this, but it seems like it was kind of a lot. It took us until after the end of the semester program. We had some epic Zoom meetings trying to handle the last few things. I mean, fortunately, Mario's up all night, so the time difference worked perfectly. Anyway, we finished it. Then we PR'd this into MATLAB because as a corollary of the adjunction we built, we could prove that the category of categories has colimits. We thought this would be something that other people might care about. So we went through the PR process, which took about 6 months. We wrote a paper about it, which is 16 pages. So there's a 16 times scaling factor from the initial pen and paper proof to the pen and paper account of the formalization. And I mean, part of it is the paper is directed at a slightly different audience, but we also discussed a lot of explicit challenges that came on the way. So the proof is exactly the proof that's sort of mentioned in that there, which I now understand much better than ever before. But there's a lot here. So this is just an illustration of this idea of invisible mathematics. So what happened here? And I'm not just going to talk about this example, but some related examples. So the plan for the talk is I'm going to give, I guess, not so much a taxonomy, but a bunch of case studies of different areas of invisible mathematics. And then at the end, the whole point of this workshop is to talk about sort of big proofs, big formalization projects. And I'm involved in a couple formalization projects. So I'll mention them at an end and some of the challenges that we're facing because of this invisible mathematics. So, I mean, we're trying to formalize some infinity category theory, kind of like the Langland stuff that Kevin was talking about in the last talk. The papers in this area tend to be very long, and so how on earth are we going to formalize anything at all? A great question. Okay. So here's just so what I'm going to describe now is a bunch of different sort of invisible issues, meaning things that are not so apparent on paper but come up in formalization. The case studies all come from category theory, so I'm going to explain just a little bit of category theory. So, I mean, firstly, the thing about category theory, you could say it sort of eats itself. So the basic data of a category is given by some objects. You think of some sort of mathematical objects, and then some sort of arrows between them. So an arrow always has a source object and a target object, and you have composition and identities, and so on. And not quite the first example, but maybe the second example of a category is the category of categories itself. So a category can thought of as its own object, and then the morphisms between them, the arrows between them, are something called functors. Okay. So in MATLAB, this category of categories is extremely difficult to work with, and it has to do with different ways that the data of a category and a functor is encoded. So sorry, MATLAB is Lean's mathematics library. A lot of these examples are going to come from Lean. One thing is that the way that so I mean, the full data of a category is quite involved. You've got the type of objects, you've got a dependent type of arrows, you've got a composition function, you've got explicitly chosen identity elements, you've got a whole bunch of axioms. And every time you want to work with a category in MATLAB, you don't want to explicitly enumerate all of that data, you just want to sort of name the category and have it kind of come along for the ride. So the way that's implemented is that you define a type that's essentially sort of an alias for the entire category structure. So you sort of give a new name to its type of objects, and then there's sort of an instance of all of this structure. I don't really know what an instance is formally, but it sort of gets carried along. So when you refer to that type, you're implicitly referring to the entire category structure. But that's not what an object of cat is. An object of cat is it's that type of objects bundled together with all this additional data that I just mentioned. And somehow when we're proving theorems about the category of categories, we're working with the objects in a different way than the mathematics library typically works with them in this sort of unbundled form. And that issue propagates to functors. So functors come with two different notations depending on whether they're thought of as functors between categories in sort of this unbundled sense, or whether they're arrows in the category of categories. There's also distinct notations for composition. So for people who are new to MATLAB, this is the weird composition symbol that they chose for whatever reason, but this is functor composition. This is the generic symbol for identities in a category. This is the identity functor. And so here's an example of something that Mario and I formalized en route to the result that I just mentioned. So the junction between infinity categories and one categories passes through an adjunction between categories and reflexive quivers or reflexive directed graphs. We had to formalize that as well. Part of proving something as an adjunction is we verify triangle identity. So this is a commutative diagram of functors. So what we're doing is we're checking that some diagram inside the category of categories commutes. And what I've highlighted is sort of all the sort of invisible lines that just absolutely should not be there. So if you're explaining a diagram chase to a student, there are a couple of steps here. Those are the sort of unhighlighted things. But these rewrite cat identity equals identity, cat comp equals comp is telling Lean we have to convert between the one notation for the functor and the other notation for the functor, because it's given one notation because our setting is we're in the category of categories, so it's thinking about composition and identities in a category of categories, but all the lemmas about categories and functors and stuff are proven in the other notation. And this drove me completely nuts. So sort of a non-trivial issue of encoding. Okay. So you might think that this is sort of an example of kind of bad design in the library, but actually there's a good reason for all of this, which has to do with universe levels, which is the second issue I wanted to mention. So strictly speaking, the notion of functor that has the funny double right harpoon thing is a more general object than an arrow in the category of categories, because to specify a category, you specify the universe level. We're referring to sort of sizes of sets or types. So you have to specify a universe level for the type of objects, and then another universe level for the type of morphisms, and then you have a category which contains the categories at those two universe levels, whose functors will then be between categories with those two universe levels. But one thing that I wasn't really aware of until I started trying to formalize some category theory is how many sort of naturally occurring examples of functors there are where the sort of universe levels of the sort of source and target are related in some sort of complicated way. So the general notion of functor in MATLAB has 4 universe levels, 2 for the target category, 2 for the source category. And so it is good to develop most of the infrastructure from that point of view, not in CAT. Of course, this is not how this is treated on paper. So rather than pick on somebody else, this is what I write in category theory and context about universe levels. So I quote Eilenberg and McLean, so I don't have to completely embarrass myself. Right. So Russell's paradox implies that there's no set whose elements are all sets. This is the reason why we've used the big word collection, blah, blah, blah. I mean, this is supposed to be a text for advanced undergraduates. So Eilenberg and McLean sort of take the point of view, which is sort of an interesting one. I mean, they say the whole concept of a category is essentially an auxiliary one. The basic concepts are essentially those of a functor and of natural transformation. That was very much their point of view when they these are the founders of category theory, writing in 1945. The idea of a category is required only by the precept that every function should have a definite classes domain and definite classes range for categories that are provided in the domains and ranges of functors. Thus, one could drop the category concept altogether and adopt an even more intuitive standpoint in which a functor such as Ham is not defined over the category of all groups, but for each particular pair of groups which may be given. I've heard this kind of point of view used by set theorists that say you don't actually need to add additional axioms to set theory because any proof itself is sort of finite and it's not sort of reaching these large cardinals that we're worried about. So What I wrote is, blah, blah, blah. The search for the most useful set theoretic foundations for category theory is a fascinating topic that unfortunately would require too long of a digression to explore. Instead, we sweep these foundational issues under a rug, not because these issues are not serious or interesting, but because they distract from the task at hand. So, and then the footnote sort of mentions inaccessible cardinals as if absolutely pressed. Okay, but I mean, of course, this doesn't work in a proof system. And I, just as a user, I find myself sort of drawn between kind of two poles. On the one hand, I'm extremely, I wrote a book on category theory, and I don't understand really which categorical constructions have which implications on universe levels. This sort of thing mires me in my formalization all the time. So, so on the one hand, I feel like I should respond to this by just actually learning how universes work in category theory, and that's definitely an approach. On the other hand, when I'm stuck in the middle of a formalization, I'm trying to do something else, which is sort of the thing that's kind of more interesting. And I feel like these universe levels really are a distraction from the task at hand, and I don't have the optimal skills to kind of zero out the universe levels, complete the formalization, and then come back and fix the universes, which would be a better practice. And in particular, there's this, some proof assistants implement sort of type in type, which is this inconsistent axiom that allows you not to worry about this, and I'm increasingly tempted. Okay, so there are two open. I don't have anything. I could highlight some examples here, but I think the examples of issues with universes are well known. So let me just say instead, there's an open question or two open questions related to the practical treatment that I would really like to answer. So one, as a formalizer, how can I sort of temporarily, what are some practical strategies for organizing the universe issue or separating the universe issue from the thing that I'm trying to formalize? Often I'll get some opaque error and I'll realize later it's a universe error, and I'd like to sort of be able to move on. But also I'm contemplating revising the category theory book, and I have no idea what I should do about the universes there. I mean, on the one hand, I'm tempted, like this is the opportunity to get it right and explicitly annotate with universe levels every result in that book. On the other hand, like do people actually want to read that? I have absolutely no idea. So I leave these as questions. If somebody could give me advice, that would be very welcome. Okay, so something else. Sophie Morel actually brought this up at breakfast today, so I'm glad we agree. So these are about invisible inclusions. I could be talking about coercions, but really I mean sort of something explicit, which is subcategories. So in category theory, we have these categories that have objects and morphisms. A subcategory, and in particular a full subcategory, is defined by just restricting to those objects that satisfy a certain property, and then taking all the same morphisms between them as before. So it's a pretty simple construction that in paper is kind of totally invisible. I mean, it's very easy to pass from a category to its subcategory. You're just looking at some small portion of the category. And this has come up in formalization for me in the following example. So some of the data that's used in one of the definitions of an infinity category, in particular the definition that's in MathLib, involves something called a simplicial set. And what that is it's a functor. So it's a functor valued in types whose domain is something called the simplex category, really the opposite of the simplex category. I've written that delta, which is the way you would write it on paper. But some constructions involving simplicial sets require only the data of a subcategory, so a restriction of this to just some data. And in particular, so the objects of this category, delta, are natural numbers, 0, 1, 2, et cetera. And the constructions that I'm interested in are restricted to the subcategory of two truncated simplicial sets. So this is the subcategory spanned by just three objects, 0, 1, and 2, which I'll denote in that way. Okay, so on paper, the subcategory has just three objects, the natural numbers 0, 1, and 2, which I've mentioned. And then it has the morphisms between them, and those are just inherited from delta. But in formalization in MathLib, the objects are natural numbers together with a proof that this is less than or equal to 2. And actually, in a lot of constructions involving the subcategory, the number m is the implicit argument, and the explicit argument is the proof that m is less than or equal to 2. So this causes all sorts of problems. I mean, on the one hand, like in the process of formalizing, I have to find proofs in MathLib that 0 is less than or equal to 2, and 1 is less than or equal to 2, and 2 is less than or equal to 2 all the time. I don't remember what these proofs are called, and what I do is I sort of state that hypothesis and do exact question mark, and whatever it spits out I put there. There are also some tactics for this, but in a formalization then I'll be trying to, I have I think in my head, a proof that x is equal to y, and I'll try to rewrite along the proof that x is equal to y, but it turns out that x somehow in it involves some proof that 0 is less than or equal to 2, and y, or the thing in the goal involves a different proof that 0 is less than or equal to 2, and then so this doesn't work unless I do an expensive rewrite. I don't know. I mean, in particular, one thing that we found is we have to, so I think this is an issue that an X would not cause such a headache for an expert formalizer, but for somebody who's just a poor mathematician trying to use a computer proof assistant, it's a huge, huge nightmare. I mean, one thing we've discovered is we have to duplicate a lot of infrastructure. None of this code should exist. So this is code that Mario and I wrote, I should say. So why shouldn't it exist? So essentially what we've done is we've taken a bunch of lemmas that are proven for the larger simplex category. So these are the identities between the generating face and degeneracy morphisms, if you know what they mean. And we're reproving them in the setting of two truncated simplicial sets because we were sort of unable to use them in the original form in our formalization. I mean, you can use them, but with sort of a lot more lines of code to tell Lean that we're not actually in the subcategory anymore, but we're in the ambient category, and therefore you're allowed to rewrite along this lemma. But there's a whole bunch of these, and I mean, this file changes all the time, you know, where people add new and new simplicial identities, and so we didn't take a screenshot of it and duplicate everything in the two truncated setting. But even if we had done it, it would be out of date now, and there's just a lot better infrastructure in the simplicial sets. And it's tempting me to sort of prove kind of less general theorems that work with the larger category and just ignore some of the data than kind of the correct theorems that work with the smaller category, just because the formalization is so much more annoying. Also, of course, there's always the question when you're doing a formalization, whether you're doing sort of the practical or the thing that you need for the objective that you have, or the thing that MathLib might want for the broader community. So these results are proven just for two truncated simplicial sets, but there's an equal notion of n truncated simplicial sets for each n, and we would have done better service to the community had we done all this in the n truncated setting, but we didn't. So, okay, so another issue, I mean, this one's a little bit different in that it relates specifically to the different formal systems that are used in Lean's, in the Lean proof assistant and many other proof assistants, and the sort of implicit set theoretic foundations used on pen and paper. I'll mention now, so this has to do with the treatment of equality, and particularly equality in dependent types, and I'll mention how this comes up in category theory. So firstly, so one of the kind of main new ideas of category theory is something called a universal property, which is a way to make a mathematical definition. So it's a way to define an object in a category even before you know that that object actually exists. And what it does, though, is it only characterizes that object up to isomorphism, or maybe unique isomorphism. It will never distinguish between two isomorphic objects, and for that reason, sort of categorical statements that refer to an equality between objects are called evil, because maybe to really get an equality rather than an isomorphism between objects, you end up making some sort of unnatural choices. There's sort of issues of constructivity here. And an example of something that is evil that, of course, comes up all the time is equality between parallel functors. So if you have two functors that go from C to D, it's certainly mathematically meaningful to ask for them to be equal. What that means is, so a functor is something that will send the objects of C to the objects of D, and those functions need to be equal, meaning pointwise equal, meaning for any object x in C, f of x is equal to g of x as an object of D, and that's the evil bit, is the equality of objects there, and then there's a mapping of morphisms. But what's funny, so this is something that category theorists joke about all the time. You should try to do no evil when you're doing your category theory. But strangely, sort of the evil equality between objects is the easiest part to formalize. The thing that is more difficult is after you formalize an equality of objects, figuring out what's going on with the morphisms. So let's say that we have our functors f and g, and we've proven already that f of x is equal to g of x. So the other part of the requirement that the functor f is equal to the functor g is that for any arrow, little f, f of that arrow needs to equal g of that arrow, or that's what it is on paper. But in dependent type theory, the way categories are defined in the dependent type theory in MATLAB, these Hom types are dependent types. So the arrow f of f is an arrow in the type of arrows in D from f of x to f of y. The arrow g of f is an arrow in the type of arrows in D from g of x to g of y, and those are different types. Because f of x is equal to g of x, maybe by a term in an identity type, by an explicit proof rather than definitionally, often in practice. So I think homotopy type theory provides some sort of intuition for what you need to do here. It's like we have terms in two different fibers of a fiber bundle, and we have some paths in the base space connecting the point on one to the point of other, and you're using something called the transport function to move the arrows before you can even compose it. So the statement that f of f is equal to g of f does not even type check. So using this evil hypothesis that for all objects x, f of x is equal to g of x, that's actually what it looks like in MATLAB. There are various ways to conclude that one functor is equal to some other functor. So these are sort of screenshots from Lean's mathematics library. So in each case, f and g are parallel functors, and the conclusion is f is equal to g. So these are different strategies provided in MATLAB to prove that one functor is equal to another functor. All of them take as this hypothesis that for all objects x, f of x is equal to g of x. But then there are various additional hypotheses which have to do with the fact that actually just the statement of what it means for functors to be equal, kind of the premise part of this is more involved in this formal system. So the thing that I mentioned about your, kind of transporting the f of little f to g of little f is implemented by this thing called Encoding, which I'm not going to explain here. There's also this notion of heterogeneous equality, which is a type that essentially expresses the idea of identifying two terms in different fibers, or so two terms in different type families. And then there is, kind of this thing that's a little bit more appealing from a categorical point of view, where to prove that f is equal to g, ultimately you first construct a natural isomorphism between the functor f and the functor g. Then you show that the mapping on objects are in fact equal. And then you check that the components of the natural isomorphism, so that's E Hom at x, that's the component at x of this natural isomorphism, are equal to the arrows that one gets from the equality through this Encoding, which converts an equality to an arrow in a category. So that's certainly not a statement I would have ever thought about in sort of pen and paper category theory, but one of these things that arises in formalization. Okay, so the next example I want to talk about goes under the sort of general heading of coherence theorems. This, I think, is also kind of related to some stuff that Kevin mentioned. So, there are some mathematical definitions that require a theorem to really state. And this is an example that comes up in category theory, specifically in two-category theory. So what I've drawn for you here is, sorry, categories have these objects and these arrows, as I've mentioned. A two-category also has two-dimensional arrows, and a two-dimensional arrow needs to go between a pair of objects and sort of source and target arrows. So this is kind of complicated the way that I've drawn this here, but this alpha, for instance, is a two-dimensional arrow between the object A and the object D, whose source arrow is the composite of this G1 followed by this L2, and whose target arrow is the composite of this L1 followed by this H1. So that's an example of a two-dimensional arrow, and there's a whole bunch of them in this diagram. And in a paper of John Power, there's a precise notion of something called a pacing diagram, which is essentially a bunch of these two-dimensional arrows inside a two-dimensional category that are composable. They're sort of composable for sort of a visually obvious reason. If you they're all kind of pointing in the same direction, and there's sort of no weird loops going on. And so the composite of this entire diagram will be a two-dimensional arrow whose source object is this B, whose target object is this E, whose source path of arrows is this R1 followed by this G1 followed by this G2. The equals things are identities here. And whose target is this identity followed by this H1 followed by this H2 followed by this R3. And so the coherence theorem says that this diagram here, this pasting diagram, represents a unique composite two-dimensional arrow whose boundary is what I just indicated. And this composition can be understood to be built out of more primitive operations, something called whiskering and vertical compositions. Those are the things that are implemented in MathLib, by the way, sort of whiskering and vertical composition. But, so I love these pasting diagram style proofs. Once you sort of, when you're learning category theory, one of the first things you learn how to do is give an argument by something called diagram chasing, which is sort of a one-dimensional, one category sort of commutative diagram argument. This sort of pasting diagrams allow you to generalize that to 2 dimensions. I use it a lot in pen and paper, but the very first time I tried to formalize something like this, I had trouble even just with the statement because, so depending on exactly how these whiskerings are, so firstly, like the 1 cells that we just mentioned, the 2 cells displayed here belong to dependent types. So where this alpha lives is it lives in the type of arrows from G1, L2 to L1, H1, and that's then dependent over these objects A and D. And if you have, the first rule of category theory is if you have an arrow and another arrow and they're composable just when the target of the first arrow is equal to the source of the second arrow. So here I need the target, which is a composite of a bunch of one-dimensional arrows to equal the source, which is another composite of a bunch of one-dimensional arrows. So here is an example. So this eta 1 kind of whiskered by this path should be composable with this epsilon 2 whiskered by the same paths because the sort of source and target paths agree, but it depends on where you put the parentheses. So associativity in a category is not sort of up to definitional equality, it's up to something that you're allowed to prove. And so depending on kind of how you parenthesize those things, Lean will not even recognize that these are composable because they have sort of different associated boundaries. So fortunately, somebody else had encountered this issue before me and fixed it. Yuma Mizuno has developed a lot of infrastructure for a weaker version of these 2-dimensional categories called bi-categories, and in particular came up with this clever bi-categorical composition. So this is meant to be composition for the 2-dimensional arrows that I just mentioned, and there's something interesting about its signature. So what I'm composing here is eta, which is a 2-dimensional arrow from some 1-dimensional arrow to F to a 1-dimensional arrow G, with theta, which is another 2-dimensional arrow from a 1-dimensional arrow H to a 1-dimensional arrow I, and then I'm going to get something from F to I, but no, G does not have to equal H. That's exactly because of the sort of issue that we encountered. Instead, what it's looking for is something called a bi-categorical coherence between G and H, and that means essentially that G is sort of literally isomorphic to H, and the data of the isomorphism comes from associativity or unitality or something like that. That's the meaning of bi-categorical coherence. But anyway, he sort of develops a sort of technique for writing composition in this sort of sense that is much closer to what it would appear like on paper by accounting for this sort of coherence issue. But nevertheless, it's still quite difficult to work with. So, so the way that the coherence theorem that I mentioned works is that so there's lots of, let's go back. So there's a lot of ways to take a diagram like this one and express it as the primitive operations, which are called vertical composition and whiskering. And the theorem says that all of the composite results agree. And the reason I chose this particular example is there's, if this eta 2 and epsilon 2 are the unit and co-unit of an adjunction, which is sort of what the notation is suggesting, this little middle bit here composes together to an identity and sort of collapses out. So this is one of these arguments that's very, very easy to make on paper that I can reduce this diagram. This is, I was completely unable to formalize this in Lean, but Yuma did, and but had to do this very massive calculation. So the proofs, so that's sort of the reason that the sort of one line of the proof that I just explained to you is there's some triangle identity of the adjunction, and that's sort of why everything simplifies. Everything else is essentially formally expressing every different possible, or sort of a clever series of possible decompositions of that pasting diagram into vertical composition of whiskering. And you have to sort of know, firstly you have to just kind of write down all the different ways to do that and then write them in the right order, and then you get to call some very complicated tactic called by category to sort of move from one step to another. So in any case, none of this is sort of visible in the pen and paper proof. And it's an open question to me whether this is automatable, whether there's a normal form for these pasting diagrams that would help with this. Okay, great. So another sort of issue that is invisible that mathematicians use all the time is passing back and forth between equivalent definitions. So, when I teach abstract algebra, one of the first things I teach my students is that there are two different definitions of a group action. There's the homomorphism definition, or there's sort of the having a binary operation with taking a group element and a set element and returning a set element, and you get very fluent at moving back and forth between these definitions, and that's where a lot of the magic of mathematics works. So there's this quote of Poincaré: mathematics is the art of giving the same name to different things. So when we're doing mathematics, we're moving back and forth between much looser analogies even than this, which are sort of equivalent definitions. And so an example that I came across recently, Australian category theory is sort of where sort of higher dimensional category theory is kind of at its apex. So there's no difference between the following three concepts found in MathLib. These are all referring to the two-dimensional categories that we just mentioned. So one is a category that's enriched over categories. So this has objects, and then its homs are categories whose objects are the one morphisms and whose morphisms are the two morphisms. There's something called a cat-enriched ordinary category, and the difference there is whether you start with a one category structure before you add the enrichment, and then you ask that it be compatible with the given one category structure, or if you start with the enrichment and then extract after the fact and underline one category. Or what MathLib would call a strict bicategory, but in the literature is more often called a two category. But just because I think of these three concepts as being the same doesn't mean that MathLib agrees. And in particular, one of the things we worked on very recently for the Infinity Cosmos project, which has given us a PR under review, pull request under review, is a translation, in fact, just sort of a one-way translation between these concepts. So converting a cat-enriched category into a strict bicategory. So that specific result is the one that we need for a particular objective, but of course the PR is being blocked because the reviewers say, well, why don't you sort of completely demonstrate this equivalence? Why don't you do this for these other things as well? And of course we should, but on the other hand, we're trying to make progress to a particular result, and we don't need any of this right now. So that's sort of an interesting kind of sociological question about library maintenance that I would also enjoy discussing. Okay, so another example is invisible details. So I think there's just a lot of mathematical arguments that are more complicated than I realized because I've never had to explain them to something as obtuse as a computer proof assistant. So here's an example. What I'm drawing now is some of the data in a simplicial set. So a simplicial set contains data of things called two simplices that, so two simplex will have three labeled objects, this x, y, and z, and then some labeled edges, this f, g, and this composite f and g. And when we're using a two simplex to think about a higher category, we interpret a two simplex as a witness that this diagonal edge is equal to the composite of the edges along the spine. And in a quasi-category, this is an infinity category sort of built on a simplicial set. We can fill something called inner horns. And in particular, by doing so, we can prove that this kind of composition operation is associative. And here's kind of how the proof goes. So if I start with edges f, g, h, and I have some two simplex here that's witnessing some composite fg of f and g. I have another two simplex here that's witnessing some composite, so here's the spine and that's the diagonal. So witnessing that gh is the composite of g and h. And then I have another two simplex here witnessing something f composed brackets gh is a composite of f and gh. So you can imagine these as forming three faces of a tetrahedron. This is one of these inner horns, and in a quasi-category, I can fill the inner horn to a three simplex, which will in particular give me an additional face whose boundary is displayed here. And this final face witnesses that this thing followed by this thing has this also as a composite, and that's the expression of the associativity, at least ternary associativity. Okay, so let's now try to formalize this. So technically, this inner horn, so this picture that I drew here, which is three simplices, three different two simplices. It's a subcomplex of the three simplex, so the tetrahedron that I just mentioned, that's defined by gluing together these two simplices along their boundary. So they, all three of them share this vertex x, this pair shares that edge f, and so on and so forth. To fully specify the sort of colimit diagram that does this gluing requires about 200 lines and is way above my pay grade. This was written by Julian Kamarami and requires sort of 3 open PRs in MATLib by Riehl to demonstrate the universal property that this is in fact a colimit. So to give that argument, to just say we build this shape and then we fill it is just a ton of work. And in particular, we don't have any proof of associativity of composition in a quasi-category. So we need this to get kind of the ternary case. The general statement is more complicated than this. And so there's a lot of things that on paper are not so difficult. This is left as an exercise in like most introductions to quasi-category theory that even domain experts can't formalize. Okay, and then so another thing I wanted to mention is I don't love this title, some sort of invisible expertise, but there's, if you're a mathematician working in a specific area, there are results that immediately are going to be true. And because there's some, broad general theory that implies them, but then there's the question of like exactly what aspect of that general theory you need in this specific case. If that theory does not exist in your mathematics library, do you formalize just pieces of it, or do you try to formalize the full general thing? This is very related to, it's tempting to just do the general thing and then have it properly, but of course, then you don't ever get to your actual objectives. So an example of this, and again involving simplicial sets, is their Riehl category structure, which some folks in this room might know about. But essentially what it means is, so a simplicial set is it has the data of 0 simplices, 1 simplices, 2 simplices, and so on. A map of simplicial sets, so simplicial sets are technically functors, so maps of simplicial sets are technically natural transformations, and so to define one you have to give a component for each object. These are the objects of the simplex category delta, so they're natural numbers. So I have to give a component fn from xn to yn for each natural number, and then check a whole bunch of naturality conditions. So there's sort of infinitely many naturality conditions you would have to check in theory. But a nice thing about the sort of strict Riehl category structure is that this can be done inductively. So you start by defining a map on the 0 simplices, and then you define a map on the 1 simplices, and there's sort of 2 things you need to check about this new map to say that it's compatible with sort of the natural transformation that you've defined previously. So to go from level n minus 1 to level n, we define a new component, and then check that this respects something called the degeneracies and faces, and each of these can be encoded as single commutative diagrams. So there's only 2 squares you need to check commute rather than, kind of very large number corresponding to all of the morphisms. Large finite, but still finite. And these 2 conditions are not necessarily insufficient. So this is a general theory that exactly explains this sort of practical problem of defining a morphism between simplicial sets. But of course, MATLib doesn't know any of this. So, do we digress to formalize this general abstract nonsense, or just check that a given family of maps does in fact satisfy a natural condition? And this issue confronted Mario and myself in the case n equals 2. So we were trying to extend the data of the f0 and f1 to add a new component f2 and then check naturality in this 2 truncated simplex category of this sort of new component. This 2 truncated simplex category has 31 morphisms, so that's 31 naturality checks. And essentially what we did is we just did them all, rather than develop this sort of general theory that says there's actually 2 conditions you need to check, and they're both true in our case. By some horrible case split. Of course, in the PR process, we were criticized for that, which is fair enough. And it was improved somewhat, but sort of not improved optimally. The result was not to go ahead and formalize the general theory that would allow you to treat this properly, just because we weren't willing to do so. Okay, and then sort of a final kind of invisible thing has to do with sort of unclear thinking. And Sophie, I should have checked with you to see if this is the talk that you're going to give here. But so some So complications with paper proofs are sort of invisible because the mathematician has not actually been thinking clearly about the issue themselves. And I mean, this is of course one case where formalization or as a proxy for explaining the proof carefully to a critical human listener can actually be extremely helpful. And Sophie gave a lovely talk about this last month. That's also a link. Okay, so I promised a taxonomy and didn't really give a taxonomy, but here's a review of some of the kind of microscopic details that, in my experience, have come up in translating from pen and paper to formalized mathematics, issues involving notation and encoding, universe levels, inclusions and coercions, dependent equality, coherence theorems, maybe translating between equivalent definitions, fully explicating technical constructions, fully developing some mathematical theories or giving precise statements, and maybe a question is, should these remain invisible or be brought out into the light? And I think opinions vary depending on who is being asked. And so now I want to transition into the kind of big proof aspect of this and describe sort of how this invisible mathematics has hindered, frankly, some work that I've been doing to formalize infinity category theory. And I'll sort of summarize invisible mathematics in kind of the following way. So it causes, or really the effects of invisible mathematics, not so much what it is. On the one hand, it causes annoyances for domain experts who don't know how to handle the invisible formalization infrastructure. So, this is kind of my experience using a computer proof assistant. I can see that there's a lot of sort of technical issues that arise in the precise way that I've formalized some definition in the proof assistant, and I don't know sort of which lemmas I need to state and add to which tactics and blah, blah, blah to sort of get rid of it, So for a sort of mathematician who doesn't have the formalization expertise, that's a real issue. But then there's the other sort of invisible mathematics that gives a high barrier of entry to somebody who is a formalization expert, but doesn't have the domain expertise involving the subject that's being formalized. So a thing that I've found extremely challenging, maybe Kevin can relate, is writing a blueprint for the Infinity Cosmos project, because I'm thinking about both of these readers at once. On the one hand, there's a reader who knows the mathematics. I don't need to say too much about the proofs, but has absolutely no idea how to take this definition and write the correct, in the sense of optimal for formalization, formal definition in lean. On the other hand, there's the proofs like the one that I just gave about this associativity where you fill the horn, which is an exercise for anybody who's in the field, but contains a lot of invisible mathematics in the details. And had somebody come to me and asked for all the details, as a domain expert, I could supply them, but it's sort of hard to think about all the details until you're asked. And these documents are supposed to enable kind of collaborations that are sort of asynchronous and maybe involve people who've never met, who've never involved in a conversation. And I find that extremely challenging. So I'm going to pose by sort of addressing, at least if not answering, two questions. Sort of what does this mean for large formalization projects, and is there another way? So, so the formalization project that I've just been mentioning is something called the Infinity Cosmos project. So what it's aiming to do is use a convenient abstraction boundary, something called an infinity cosmos, to formalize some of the core category theory of infinity categories for immediate use in MATLib. So we are not going to formalize all of the results in Topos theory or Keradan. Those are not all accessible within this abstraction boundary, but there are certain things that are, and the idea is to get it into MATLib as soon as possible. So in terms of sort of the state when we started, so MATLib knew a definition of an infinity groupoid, so a weak infinite dimensional analog of a groupoid modeled as con-complexes. It also knew the definition of an infinity category modeled as quasi-categories. Both of these things are built out of the simplicial sets, which is why I was mentioning simplicial sets so often. But very few theorems have been formalized about either of these notions. And in fact, until January, the definition of con-complex was wrong in a way that would have been very obvious had anybody tried to prove anything about it, because it wouldn't have worked. And sort of why is it so difficult to work with these things? Is these are kind of these invisible, meaning steps you don't actually check all the details of a pen and paper that are extremely difficult to write down precisely. So a few years ago in a project having to do with something else, I sort of wrote a paper with some sort of fighting words, sort of despite all these wonderful things in Lean's MATLib, means that does not contain any infinity category theory. And actually, we're very close to fixing that. And in fact, I'm hoping to recruit some lean experts right now. I think with the right, so you know, the sort of invisible mathematics has really slowed down the kind of asynchronous version of the formalization project, because we have contributors coming from each community which are dealing with the issues that are sort of visible to one community and invisible to the other community. But right now we're here in person, live, and can formalize in a different mode with, you know, Mario and I, for instance, work wonderfully together because he brings one sort of expertise and I bring another expertise, and when we have a moment to sort of sit down and do things together, we can do something that's completely beyond either of our capabilities separately. So I'm trying right now to see if I can recruit somebody to help us get some non-trivial infinity category theory and lean in MathLib by the end of the week. Specifically, this is what we need. So in sort of an active work in progress, we have an isomorphism of simplicial sets at universe level 0 that we need at all universe levels. So that's task number 1. We have a component of a natural transformation that I would like to show is an isomorphism. And the domain and codomain are functors that preserve colimits, and the objects that we've applying this to are colimits. And we need to reduce the check of that being an isomorphism to the check that the components at these pieces of these colimit diagrams are isomorphisms. This is, by the way, sort of very close to the result that launched category theory, by the way. Eilenberg and MacLean were making some sort of similar argument about proving that a map between limits was an isomorphism because it's a component of a natural transformation between some diagram, and the components were isomorphisms. So essentially we need that formalized. And then we have 2 open PRs. But with that, what we would get as a corollary of these sort of kind of boring to explain technical results is that there's a strict bi-category whose objects are infinity categories, whose morphisms are infinity functors, and whose 2 cells are infinity natural transformations built using quasi-categories. And in particular, MathLib already knows about adjunctions in a bi-category, and that definition will specialize to give the correct definition of adjunctions between infinity categories. There's also some theorems about adjunctions, about mates, and so on. So we would get some non-trivial theory of adjunctions between infinity categories if somebody can help me complete these tasks. Okay. So the other thing I wanted to address, though, is there another way? So is there a way to kind of sidestep this invisible mathematics whatsoever? And I'm going to motivate this by a sort of appeal to authority. So I guess Vladimir Borvatsky, I don't know if he discussed this at the Big Proof workshop a while ago, but he wrote this lovely essay describing the origins and motivations of univalent foundations, or homotopy type theory, by sort of lamenting that a technical argument by a trusted author, which is hard to check and looks similar to arguments known to be correct, is hardly ever checked in detail. So his personal experience with some mistakes in high-profile papers led him to abandon pen and paper mathematics in favor of computer formalization, but he did not try to formalize his kind of theorems of higher category theory in a proof assistant like Lean. I mean, Lean didn't exist. Instead, what he did is he invented a new foundation system in which the basic objects, these types, are meant to be thought of as something more complicated than sets, something like homotopy types. And what is a homotopy type? The point is it's a mathematical object that is much more complicated to define in set theory, but is a lot closer to the objects that he was trying to study. So homotopy type theory, univalent foundations can be thought of as a foundation for all of mathematics, but really it's also a domain-specific language. It's a foundation that's meant to make it a lot more efficient to reason formally, so with the aid of a computer proof assistant with all of the details fully sped out about higher structures, but I'm not compiling everything all the way down to some foundation system that's very far away from the mathematical objects I'm using. I've sort of brought the floor closer to the ceiling. And my personal experience in this sort of synthetic mathematics is it allows proofs to be both rigorous and considerably shorter, even in the formalized version, than in other areas. And in particular, the speed up, the sort of gap that I mentioned, 16 times or whatever it is, from pen and paper to formal, is much, much less in a synthetic foundation system. And to illustrate that, so, sorry, what is this other thing that I'm mentioning? So in particular, I've also been formalizing some infinity category theory in a formal system called simplicial homotopy type theory, S-hot. Cannot do this in lean because it's a different formal system. It requires a different proof assistant, but there is a proof assistant called RZK, and this is the landing page of our formalization library, smaller than MATLAB, but we have a lot more serious theorems about infinity category theory formalized already, and the formal proofs are considerably shorter. And to illustrate this, I'm going to show you a formalization of the infinity categorical Yoneda lemma, sort of a special case of it, so it's a little bit easier to explain. This is something that is completely out of scope of the Infinity Cosmos project. So what is the infinity categorical Yoneda lemma? So it says, so all of these screenshots are of RESC formalizations. So given a pre-infinity category, you don't actually need a full infinity category structure A and two objects A and B. We have a type hom A, little b of arrows from A to B in A. And the statement of the Yoneda lemma is this type is equivalent to the type of natural transformations between the contravariant representable functors at A and B. And one of the things that reveals how much simpler this synthetic language is to work with is what I've written here is really a type of functions. This is, so natural transformation phi, you can think of as some function that takes another z in A, and then an arrow from z to little a, and returns an arrow from z to little b. Usually that's just the components of a natural transformation between representable functors, and then there's like a naturality condition, but that actually comes for free here. So this thing is the type of natural transformations. And so really what I'm trying to do is construct an equivalence between this type and this type implemented by some function called contra evid. So this is the entire proof, but now I have to tell you about what those four pieces are. So what is an equivalence between types? Well, it's a function in each direction. So I need a function that takes one of these natural transformations phi and returns an arrow. And if you've seen the Yoneda lemma, what you know is you're supposed to take this phi and then evaluate it at the identity arrow. So that's how you get an arrow here. The identity arrow at little a gives you an arrow from A to B, and that's the arrow you return. In the one categorical proof of the Yoneda lemma, it's not so difficult to define the function in the other direction. In infinity category theory, this is usually quite difficult. But in this formal system, you can just rewrite the one categorical construction and it works. This is sort of, again, the magic of having a domain-specific language. This all gets interpreted, by the way, in the complete Siegel space model of infinity categories, or for internal infinity categories, in fact. So here, how do you go the other way? If I have an arrow V, then I take an object Z and an arrow F from Z to A, and I just compose F with V, and that returns an arrow from Z to B. That's how you define the natural transformation in the other direction. And then I just need to check that these two functions are inverses, so inverses pointwise. So in one case, this just follows from the identity law, which interestingly is a theorem rather than an axiom about pre-infinity categories. And then the other case, it's a little bit more complicated. So here I'm starting with a natural transformation phi, and then I sort of pass across the equivalence to get an arrow and then rebuild a natural transformation, and I need to check that they're the same as functions. So given an x and an f, phi of x of f is the same as the result of the natural transformation the other way around. And there's two steps here. So this is the longest part of the proof. So I'm using naturality, and I'm using an identity law again, and then function extensionality to complete it. But the point is, this is a complete formal proof, and the gap between this and the pen and paper proof is much, much less. So that's some food for thought. I'll stop here. Thank you.
Thanks a lot, Emily. So do we have questions for Emily? Kevin, question?
So could you write RISC in lean? Can you write a domain-specific and then translate everything over?
Yeah, I would love to try something like that. So there's a project that's in that spirit, which is the Hot and Lean project. So Sina Hazrat-Pur, Steve Awadeh, a bunch of others are working on this. And if that is successful, this is what I want to do next, for sure. Interpreting fully into the model would be quite difficult, though. Okay, so but yeah, we can discuss later.
You've been doing a bunch of stuff with bicategories, right? Which is kind of quite painful, and will get much worse if you're trying to do tricategories. Do you think there's room for sort of switching to like theorem spaces or higher Siegel spaces?
Yeah. Right. So folks, let me reinterpret your question. So the aspects of higher category theory that I've mentioned in this talk are considered the easy ones. So sort of two-category theory and infinity category theory are the two easy cases of higher category theory. So tri-categories or theta n, infinity n category theory are considerably more difficult. I'm having enough difficulty with this. I don't have ambitions to try the other things, but of course somebody else should.
Do you know the problem of definition equality in this proof system?
Sure. So yeah. So this proof assistant is it's essentially implementing kind of homotopy type theory with some additional shapes in the context or something like that. We have the definitional equality layer like in Wien's type theory, and then there's the sort of type equality layer, which does not have uniqueness of identity proofs, but it's still the Martin-Liff identity type. I mean, I guess if you're used to writing sort of proofs in hot, this is a lot like this. If you're not used to writing proofs in hot, you might be a little sad about some coherence things you have to check, but I don't know. It hasn't been so bad from my point of view, but it doesn't sidestep that issue, I should say.
Yeah, maybe a speculative question. But you mentioned at the start that these pieces of invisible mathematics are a roadblock to auto-formalization. Do you think mapping out what kind of invisible aspects of mathematics there are is a path towards fixing that hole, or do you think it's just irreparable?
No, I mean, I'm sure it's not irreparable, and my instinct would be it would help if we understood this better before we tried to get a computer to understand this better. So I absolutely agree with that. So,
yeah, so on the notion of invisibility, so I mean, most people, at least for me, haven't studied infinity category theory, so don't know how to prove results in infinity category theory. So you mentioned there was a nice pairing with you and Mario. Mario doesn't know anything, doesn't know as much as you do about category theory.
It doesn't know anything is correct.
But the idea of what it means to come to know some piece of mathematics or come to have some sort of compressed, compact model for which you can either easily evaluate that a statement should belong to something that's coherent with the rest of what you know, even if you don't necessarily know how to kind of implement all the particular details. Sounds maybe a bit like training on a bunch of data and then seeing does this match a lot of patterns that you've seen about other related theorems, and then trying to kind of extrapolate and say that this is how it should proceed from here. And I guess the idea of having all this invisibility is one who doesn't have coming in having any kind of coherent model of what should be the objectives and just literally just verifying step by step as though there's no coherence. Is that sort of what you kind of have in mind with this invisibility?
Sure. I mean, I guess, really a lot of this talk was motivated by my experience with this Infinity Cosmos project, which is the attempt to formalize infinity category theory in Lean. And I think I'm just doing a terrible job at leading it for a lot of reasons. Some having to do with how much time I'm devoting on this versus other activities. But I think a lot of it is I just don't understand well enough what I need to explain to which constituency. And I don't know if it's entirely my fault or there's sort of something about...
But there's some property about the mental model in which you have that it's hard to kind of remember what it was like to not know how things should fit together.
I think possibly, and also part of it is I'm really just coming from one side. So, if I had equal expertise in computer science and formalization, if I had any idea how these proof assistants actually work, I think, I'd be able to sort of offer better guidance on that aspect of it too. But a lot of this is invisible to me as well as to anybody else I'm trying to communicate with.
Anyway, so maybe a related question is, do you feel that you've learned some mathematics in this project? And maybe also a different aspect of the same question is apart from this universe stuff, would you know write category theory in context a bit differently after this experience, or would you still write it the same way?
No, well, right, interesting practical question, and ask me again in a few years. Because I do intend to do a revised version. I'm sure there are things that would be different. I mean, one thing that formalization has helped me with, of course, is just being more precise about statements. You know, like an explicit mapping and equivalence versus there is an equivalence or something like this. So that certainly I'll clean up. Yeah, I mean, of course, any proofs that I formalized, I feel like I understand much better than I ever did before. And yeah, but I'm kind of of two minds. I mean, it's interesting to think about how, is this a selling point for the broader mathematics community, or is it not? I mean, there's an aspect of which, you know, going very deep into a bit of mathematics is what drove a lot of us to become mathematicians. But there's also an aspect, you know, of mathematics, which is about sort of daydreaming and, you know, developing such a thorough expertise in an area that you can just imagine some wildly speculative conjecture based on very thin evidence, and nevertheless it's probably true. And that seems very far removed from formalization. And I'm curious also about how kind of this big picture stuff can fit big picture and not yet finished, you know, so still conjectural as opposed to, you know, something that is a theorem somewhere, you know, how that can fit into a new paradigm of proof writing where mathematicians use a proof assistant a lot earlier in the research process. So.
Yeah,
I mean, maybe just turning the last couple of questions around, let me ask you just a broad philosophical question. How is it that mathematics does so well given all this invisibility? I mean, given that it's so hard to fill in the detail, what is it that keeps it kind of coherent and falling apart?
That's a wonderful question. It's a miracle. You know, I think part of it has to do with like discovery, and so that, you know, there are things that are true that we don't understand perfectly yet, but they're still true, not because it had nothing to do with us.
Yeah, but the intuitions are coming from somewhere.
Sure. You know, I think maybe part of it is also community. Like, you know, everybody, I mean, part of what I'm pointing out with the invisibility here is what's invisible to one person and what's invisible to another person are often different things. And I think that happens within the mathematics community as well. So maybe I've checked some part of the proof, and then some grad student who read it a few years later sort of checked another aspect of the proof that I didn't check, but fortunately that was true. And then some grad student a few years later checks a different aspect and finds out it's wrong. But, you know, when that process sort of iterates, I think maybe collectively we're converging on truth that's not so well understood by any individual. So, but great question.
Let's take two last questions because then we need to have lunch. Yes?
So you mentioned the problem with universes. We did that in the hot library in Rock a long time ago. But there were efficiency issues. There's now a new algorithm called algebraic universes that seems very promising that does efficiency to solve this. Then the question is, would you consider computation as part of invisible mathematics?
Computation in what sense?
Computation as in, I have two expressions in unary numbers and I just want to add them.
Yes.
That's already very hard if the
Yes.
numbers are slightly bigger.
Yes, yeah, that's an aspect that's invisible to me that I didn't even mention, but of course, yeah.
And of course that becomes much bigger if you have more serious computations.
No. Great, thanks. No.
Filippo, any last question?
So you started speaking about invisible mathematics or invisible mathematical experience. One thing that is very visible formalization is the use of tactics. So I was wondering if you think that tactics can be, or an inspection of the tactics you use, can be used to organize your taxonomy of invisible mathematics.
Yeah, that's another interesting suggestion. I'll confess to feeling a bit uncomfortable with tactics because, you know, I like this idea that in formalizing a proof that I understand it better than before, but if part of my formalization involves calling a tactic that I didn't write, which is all of the tactics, then I feel like there's an aspect that I don't understand. So yeah, in particular, whatever SIMP is doing is completely opaque to me and seems to change regularly. So yeah, I don't know. But anyway, it's an interesting suggestion. And of course, you know, there's another question of like, do we want this to stay invisible, or would it be nice if we could make some of the stuff that became visual through the pain of formalization invisible again, and tactics are often mentioned as a solution to that problem. I don't know personally how I feel about it, but of course, it's wonderful to have a nice tactic, and I don't mean this to slight the people who are writing these tactics that we use all the time.
Okay, so thanks again.